conditions. Chapter 1, Understanding Weather and Climate. What is meteorology? Meteorology is the study of all interacting processes which work in concert to provide us with the conditions we commonly ask people about. What is weather? Weather refers to those characteristics we commonly ask people about daily. How is the weather where you live? Is it raining there? Our day is hot and sunny. It's the daily conditions of our atmosphere. Climate refers to the seasonal changes in weather over a long measurement period, such as a year, a decade, or a century. We adjust our seasonal shopping habits as a function of climate. We buy warm clothes for winter, swimsuits for the summer. Now there is some debate about what is an appropriate amount of time to measure climate. We do have a lot of tools available to us. We will cover some of those tools and analysis techniques later on in the course. But some people will look at climate over a period of a year, which seems too small to me. Even a decade doesn't seem long enough. Usually about 50 years is a pretty good snapshot. It's a good place to begin. If we go back too far, we run out of actual scientific data that we can use. We have to use people's journals and the recordings of individuals rather than any kind of national endeavor to collect data in a consistent way. And then we can go back into lots of different environmental records to determine previous climates. How high is the sky? Now, that is a question that children often wonder about, and they'll ask their parents how high the sky is. There is no universally accepted definition of how high the sky is, but obviously it doesn't go on for infinity. For our planet, the general rule of thumb is that our atmosphere ends, or the top of our atmosphere ends about 60 miles above the Earth's surface, or about 1,000 kilometers, or if you want to think about things in terms of feet, it's a little over 300,000 feet above the Earth's surface. So that's where the boundary between the atmosphere and space begins. There are two primary layers of the atmosphere. There's the homosphere, which exists from the ground to about 50 miles above the Earth's surface, or about 80 kilometers. Within the homosphere, there are elements which comprise the atmosphere, and those elements are uniformly mixed. So we tend to think of our atmosphere as, it is dynamic, but we tend to think of it as this constantly changing chemical mix of atmospheric molecules. And the reality is that the homosphere where we live, it's generally uniform. The atmospheric chemicals and molecules are generally uniformly mixed. The other primary layer, which exists above the homosphere, is the heterosphere, where atmospheric gases organize themselves and settle out by their molecular weights. So nitrogen and oxygen have higher molecular weights than, say, hydrogen and helium, and so those are going to settle down to the lower part of the heterosphere, whereas hydrogen and helium, which are lighter, are going to be found in higher proportions at higher altitudes. Permanent gases are pretty much exactly what they say. They're permanent gases. Sometimes you'll see them referred to as constant gases, but these are atmospheric gases which are present and have been present throughout much of Earth's history, and their composition and amounts generally haven't changed that much over hundreds of thousands of years. So we're talking about gases like nitrogen, oxygen, and argon. Now, if we've got permanent gases, there must be some other gases that are more variable, and sometimes you'll see them referred to as volatile gases. These gases, the amounts of them, and the composition, their presence in the atmosphere changes over time. So we have differing amounts of carbon dioxide, we have different amounts of water vapor, methane, and ozone. And not only do these amounts change over time, but the composition, their presence in the atmosphere will change depending on your location. So, for example, water vapor, there's the equator and the tropical areas of the Earth contain more water vapor than areas that are closer to the poles. So once you get towards the North Pole and the South Pole, the air is drier and there's less water vapor. So your location also matters. Why is water vapor so important? You're probably going to become tired of hearing about water vapor, but water vapor is a significant contributor to the dynamics of our Earth's atmosphere. Even though it only represents 1/4 of 1%, or about 0.25% on average of our atmosphere, it's one of the leading forces that drive both climate and our daily weather. Water vapor is more common at the equator. As I said on the previous slide, it's less common at the poles, but water holds heat energy very well. It's also the source of clouds. And so when those two things work in concert with each other, you have water vapor, which absorbs heat energy very well, and then the water vapor is also a component, an ingredient in clouds. Clouds absorb heat energy. Clouds absorb thermal energy. But clouds can also reflect solar energy as well too, and so it becomes a very complicated set of circumstances which drive our atmospheric heat engine. Carbon dioxide is another important molecule within our atmosphere. If you could capture a million molecules of air, and that might be kind of hard to do, but if you could capture a million molecules and count out a million molecules, only 390 of those molecules would be carbon dioxide. So another way of phrasing that is 390 parts per million would be carbon dioxide. Now, carbon dioxide comes from most natural processes, including man-made or anthropogenic factories or automobiles, but they're also created by natural processes. And then plants also take in carbon dioxide and give off oxygen in their metabolism. Ozone is another important component to our atmosphere. Ozone is toxic to life. It irritates our eyes, causes asthma, can kill vegetation. It's not very good for us. Ozone can be produced by automobiles and by certain other natural occurring processes. But ozone is very important to life on the planet, as long as we don't breathe it, because it blocks ultraviolet radiation. Ozone forms when single oxygen atoms smash into oxygen molecules. This happens in the stratosphere. The stratosphere is part of the ionosphere, and we'll talk about that later on in this slide presentation. But this happens in the stratosphere where atmospheric density is less. And so we'll talk about density in a little bit, but when you have less dense atmosphere, you have a lot more room for molecules to fly around. Eventually these molecules will smash into each other. Their electrons will break free. Some of these ionized molecules will bump up against atoms, and then they'll take on that extra free electron from the atom that's out there cruising around after it's been broken apart by solar radiation. So the ozone gets developed or gets created in the ionosphere. Why is methane important? Well, methane is not particularly toxic to life. It's explosive, so in that way it's sort of dangerous. If it becomes too great in proportion to the amount of air around it, you can pass out. But methane is very good at absorbing solar energy too, thermal energy from the sun, which makes this gas important in atmospheric warming. So you can see that there's a trend here. We've talked about ozone, we've talked about water vapor, we've talked about CO2, and one overarching theme that you should pick up here is solar energy and thermal energy is very important to our atmosphere. Aerosols. What are aerosols? Aerosols are microscopic bits of solids and liquids. They're not the cloud drops, and they're not any other kind of precipitation, but they can create circumstances where precipitation can occur. So basically they act like as the core, the nucleus of cloud droplets, and they can act as the nucleus or the agent for the creation of some types of precipitation. So these can be very important. So they're solids like very microscopic dust particles, microscopic bits of liquids that have been suspended in the atmosphere, and then as these things fly around the atmosphere, they will collect other bits of liquids and other solids, and eventually through a process, there's a couple processes in which the precipitation and these droplets form. One of them is called accretion, and they'll essentially build up to something, to some type of precipitation, and perhaps even condense out and fall as rain. Why is density important to our understanding of the atmosphere? Okay, there are two really important traits associated with the atmosphere. There's density and there's pressure, and both of those are highly related to one another. Okay, so density is really just, if we can understand how it's expressed, as mass per unit of volume. So we have some mass, we have some weight, and then we have a unit of volume. So usually you can look at the units in which the term is expressed. And so in this particular case, we have pounds per cubic foot. In the metric system, you'd have kilograms per cubic meter. And so it's essentially the amount of something that you have within a certain volume. And so if something is really dense, say lead, if you had a shoebox and you filled it full of lead pellets and you picked it up, that's going to be very dense. You've got a lot of material in a very small volume. Okay, now you're going to take that same shoebox and dump out the lead, and then you're going to fill it full of Cool Whip. Okay, it's not going to be as dense because the Cool Whip there's far more space inside that Cool Whip between the atoms and the molecules of that Cool Whip than you had in the lead. So the density of that shoebox has been decreased greatly. So part of the understanding of density is we can see in the spring and sometimes in the fall when we see hot air balloons, because that's part of the reason why hot air balloons float, is because the density of the air inside the balloon is less than the density of the air outside. But density is very important when we talk about atmospheric qualities. As we change our altitude, as we change our elevation, the amount of air molecules becomes less per unit of volume. Now we sort of have to be careful here because densities can change, depending on location and depending on the temperature and the water vapor and the density of the atmosphere in our particular area. So these are general traits. But generally, as we change our altitude, the number of air molecules becomes less per unit of volume. So, for example, in Memphis is about 330 feet above mean sea level. We're going to have the amount of air molecules in Memphis is going to be greater than what you would experience in Denver, Colorado, which is about 5,000 feet. And then La Paz, Bolivia, which has the distinction of being the highest capital, the capital in the world at the highest elevation, which is about 13,000 feet. So we're almost about 3 miles above mean sea level. So at La Paz, Bolivia, it's relatively hard to breathe because the density of air is much less than the density of air in Memphis. So gases are compressible too, meaning we can add more gas, we can take gas away to any given container, and thereby we can increase the density. But we have to also bear in mind that several things can happen when we modify this density. And when we modify density, we have to start talking about changes in pressure. Why is pressure important to our understanding of the atmosphere? Pressure is generally expressed as some force per unit of area, such as pounds per square inch. For weather and climate studies, we generally use the units of millibars, which is expressed as a lowercase mb, and kilopascals, which is expressed as a lowercase k, capital P, lowercase a. Those units are used. At sea level, atmospheric pressure is about 1,013 millibars, or about 101.3 kilopascals. Okay, just keep that in mind. It's about 1,000. So if you roughly think about sea level pressure, like if you're at the beach, you're at sea level, the atmospheric pressure around you is about 1,000 millibars. So that's essentially like what the next part says. When you go to the beach, you're at sea level, and you have about 14.7 pounds of atmosphere pressing down on every square inch of you. Now, we're used to this. We grow up in this. Our body's acclimated to this. But if you were to go to Denver or go to La Paz, that amount of atmosphere that's pressing down on you is going to be different. So it's not going to be 14.7 pounds anymore. It's going to be less. However, and this is what can get people in trouble when they scuba dive, now you're in a fluid that has considerably different density, greater density than that of the atmosphere, and that's why the density of oceans and scuba diving and diving in general becomes a problem, because our bodies aren't exactly acclimated to that type of pressure, and that can change the blood gas chemistry in our bodies. But as your altitude changes, the amount of atmosphere above becomes you less, and thus the pressure is less. Pressure change is not uniform as altitude increases. It's logarithmic. So atmospheric pressure falls by 50% for every 3-mile increase in altitude. So for example, at 15,000 feet, air pressure would be about 506 millibars. Okay, so what we've done is at sea level, we're at 1,000 millibars approximately. Now, the rule of thumb says it's 50% for every 3-mile increase. Well, a mile is about 5,280 feet. So I'm roughly going to say 15,000 feet. So essentially, we basically have our pressure. So it would be, if I wanted to stay technical and stay with the 1,013 millibars, then it would be approximately 506.5 millibars. But I'm rounding here to make the math a little easier. So at 15,000 feet, air pressure would be about 506 millibars. At 30,000 feet, it's going to be half the 506, which is essentially about 253 millibars. So if you want to convert that to kilopascals, you basically would move the decimal point over, so you would have about 50.6 kilopascals and about 25.3 kilopascals. Now, the atmosphere has 4 layers, which are strictly defined by temperature and how the average temperature changes as altitude increases. And we'll talk about how those measurements take place later on. So the first layer of atmosphere that we have, which is essentially from the surface of the Earth to approximately about 6 miles above the surface. Now you'll see references to where it's anywhere from about 3 to about 12, and that depends a little bit on some of the chemistry involved in the atmosphere, because we are talking about temperature, and temperature is affected by water vapor and the presence of some other gases like methane and carbon dioxide and things like that. And so sometimes it's going to be as low as 3 miles above the surface, and then troposphere could begin about 12 miles above the surface. And if you think about where those areas might be, because we are talking about temperature and we are talking about water vapor and carbon dioxide and methane, you can kind of guess where the thin portions of the troposphere are versus the thick portions of the troposphere. The stratosphere is the next layer, so it goes from about 6 miles on average to about 30 miles above the surface. The mesosphere is the next layer. It begins about 30 miles above the surface and then extends to about 50. And then the thermosphere is the last layer, which begins about 50 miles above the surface and then extends to about 70 miles above the Earth's surface. Okay, the troposphere, we're going to go back and look at these individually. So now we have a graphic that shows us where the troposphere is between 3 to 12 miles. And generally it's going to be as the temperature decreases and the air becomes a little bit drier, the troposphere, the variance in height, the thickness of the troposphere is primarily due to temperature. So if you go back to the previous slide where I sort of had you think about where these places might be, where the troposphere is thicker and thinner, we have a lot of water vapor near the equator. Water vapor warms the air, or it contributes towards the warming of the atmosphere. And so the thickness of the troposphere is going to be greater at the equator. With a decrease in temperature, there's a decrease in water vapor near the poles, and so with less water vapor, there's not as much opportunity there for the atmosphere to become warmer, and so you're going to have the temperature is going to drop off quicker near the poles than it would at the equator. So we've got a troposphere that's thin at the poles and thick at the equator. The stratosphere exists above most weather phenomenon. Okay, so when you look at this graphic, the stratosphere basically begins, and the graphic is sort of in the way, but it's about 12 miles above the surface of the Earth. So 12 times 5 is about 60,000 feet. Okay, so where I get that is from, we've got 12 miles, and there's about 5,000 feet in every mile. So if I multiply 5 times 12, we get 60, and then add my zeros on, so I'm about 60,000 feet. And most of our weather phenomenon occurs below 60,000 feet. Heating is almost entirely from ultraviolet radiation from the sun and the reflected thermal radiation from the Earth's surface. So what we've got is we've got ultraviolet radiation directly coming in and striking the stratosphere, but then also some of the heating is coming from reflected thermal radiation that wasn't blocked on its incoming journey from the sun. It's been reflected back into the atmosphere, and now it's being reabsorbed into the atmosphere. So part of the heating is from that reflective thermal radiation. Our protective ozone layer, which is denoted in that kind of buff, peach-colored, fuzzy area on the graphic. This is where our ozone is found. Aerosols are also present here, which can block incoming energy from the sun. They can find their way into the stratosphere. Whenever we have a volcanic eruption, for example, volcanoes are notorious for disgorging tons of volcanic ash into the stratosphere. And so that can distribute itself across the globe. And in fact, this has happened in a number of cases in the past and has changed climate for months or even years, to where once that ash blankets the globe, and generally this has only happened in the northern hemisphere, which is unfortunate because that's where most people live, but it acts as a cooling mechanism when it blankets the northern hemisphere. It allows the incoming solar radiation to be reflected back into space, so it never reaches the habitable layer of the troposphere, and so we end up having atmospheric cooling. And we've had some miniature ice ages occur. The most recent one occurred back in the mid-1800s, when a volcano in Southeast Asia basically erupted and basically changed the climate for about a year and a half. It was pretty devastating for the people that were alive back then. Led to a lot of deaths, famines. The third layer, the mesosphere, exists above the stratosphere and extends about 30 miles to 50 miles above the Earth's surface. The mesosphere is very cold, it's very dry, there's not really a whole lot of heating going on, at least not thermal heating. The only significant heat is due to the heating at the tropopause. So if you look at the graphic, the tropopause is the boundary between the stratosphere and the mesosphere. It's not very thick, but that's where the remaining bits of atmosphere, the air molecules that can take on some thermal properties, water, there's a little bit of remaining water vapor. That's where that heating takes place, is right there at that boundary, and then it propagates upward. The fourth layer is the thermosphere. The thermosphere is the uppermost portion of the atmosphere, of those layers that we basically define strictly by their temperature properties. The air density here is extremely low. Molecules have to travel literally miles before they will collide with another molecule. Ozone is created here due to the presence of intense solar radiation breaking up the oxygen molecules. And so we have the Earth is constantly being bombarded by radiation all the time. If you look at the electromagnetic spectrum, that's essentially what's hitting the Earth 24 hours a day, 7 days a week. And thankfully, the atmosphere reflects some of that back. Thankfully, it absorbs some of it. Thankfully, the ozone layer filters out some of the dangerous ultraviolet radiation. But some of that energy which doesn't strike the surface of the Earth and affects us, it still affects the molecules that are in our atmosphere. And that very intense radiation breaks up these molecules and essentially creates ozone, which has a side benefit of helping filter out our ultraviolet radiation.